So far we have understood what the attacks are. Now the real question is, how did researchers discover these vulnerabilities and what have they actually solved and where we are still failing? So to answer that, we need to look at the evolution of research contributions over the time. So this video is focused on this perspective. So now let's first see where the field stands today. Before going attack by attack, here's the current scientific consensus in the period of 2025 to 26. So the LLM security is not solved. Recent surveys confirm that prompt injection is still the number one vulnerability in real systems. Secondly, core truth researchers agree on this aspect that LLMs cannot reliably separate the instructions from the data. Then we have current paradigm shift. This is very important. So we are moving from prevent attacks completely to assume attacks will succeed and limit the damage. Now let's see the full timeline of LLM security evolution. The first wave is privacy and memorization. So this is 2015 to 2021. In the early days of machine learning security, researchers were not thinking about prompt injection or jailbreaks. Instead, they were asking a different question like, can models leak the data they were trained on? The breakthrough insight is that when large language models appeared, researchers found something surprising. The models could sometimes reproduce the exact training text. This was a first major warning. So research status at that time is that privacy risks were real but limited. Attacks worked best on a small and overfitted models. Large language models were sought to be safer due to generalization. So the gaps are like low clear understanding of how much LLMs memorize, no strong guarantees of data privacy, no scalable defense mechanisms. So this phase established LLMs can leak information, but we do not yet know how serious it is. Then we have phase 2, that is early LLM era, that is 2020 to 2021. This is the memorization shock. Researchers found that GPT-style models can sometimes produce exact passages from the data they were trained on. Bigger models memorize more than expected, so this created the first privacy concern wave. Then the second wave is prompt injection, that is 2022. This was a turning point. Researchers discovered something fundamentally new. You do not need to attack the model internally, you can control it using the language. The key contribution is that introduction of prompt injection as a concept. Researchers showed natural language can override system instructions. LLMs cannot distinguish trusted and untrusted input. So this was revolutionary. Before this, the attacks required access to models' internals and training manipulation, but now everyone with text input could attack the system. The research status says that prompt injection shown to be simple and powerful, and it works in black box settings, and it requires no technical access. But gaps are that no formal method to separate the instructions from the data, no reliable filtering mechanism, no theoretical framework to prevent it. Then third wave is jailbreaks and adversarial prompts in 2023. So with the release of ChatGPT, research exploded. So the research focuses on jailbreak taxonomy, including the role play attacks and persuasion attacks or multi-step reasoning bypass. Then we have evaluation studies on it, like many findings indicate that many jailbreak prompts succeed 90%, more than 90% on some models. Key realization is that safety alignment is not robust, it is only probabilistic. Fourth phase is training time attacks, that is 2024. So researchers then shifted the focus deeply into the pipeline. Instead of asking how do we attack the model at runtime, they asked, what if a model is already compromised before deployment? So the key contribution includes the data poisoning studies, in which researchers showed extremely small poison datasets can alter the behavior. The backdoor mechanism, they demonstrated that hidden triggers can be embedded into LLMs, and these triggers survive training and fine-tuning. So you do not need large-scale control to compromise a model. Even tiny injections can create persistent vulnerabilities. Then the fifth wave is focused on agentic LLM security in 2025. So now LLMs evolved from the chat systems to agent. Now models can browse web, execute the code, call APIs, read the files. So this created new attack class, that is tool plus the prompt injection hybrid attacks. For example, malicious text inside a web page, LLMs read it and executes the instructions unknowingly. The research findings indicate long context injection increases the success rate significantly, and multi-step agent workflows are highly vulnerable. So research gaps are that no secure architecture for agent workflows, no reliable monitoring of multi-step behavior, no strong guarantees on tool usage. So this phase introduces action-based risk, not just information risk. So the current frontier is the system and infrastructure security, that is the current era 2025 to 2026. The most recent research goes beyond models. It focuses on entire ecosystem, and it now includes runtime environments, container escapes, so hidden outbreak channels discovered in LLM tools environment. So key realization is that even if the model is safe, the system around it may not be. Now let's map all the attacks to their maturity level. Number one is prompt injection. So it is not solved and it is critical. Research findings indicate that it is a top risk for AI systems. These attacks still succeed in real-world applications today. They become even more dangerous in AI agents that can take actions. It persists because AI cannot clearly separate the trusted instructions from the untrusted external content. So it may follow malicious text as if it were valid instructions. Research gaps. There is no reliable method to ensure that AI only follows safe instructions and ignores the malicious ones. There is no system that can consistently detect and block all malicious prompts without also blocking normal and harmless ones. Next is jailbreaks. So the status says that it is partially controlled but not eliminated. The research status is that thousands of different jailbreak techniques exist, and many models can still be tricked into breaking their safety rules. Gaps indicate that attackers create new jailbreak tricks faster than developers can block them, and there is no single defense that works reliably against all jailbreak methods across different models. Next is data poisoning. So it is of high risk and hard to detect. Research findings indicate that even a small number of malicious or manipulated documents, maybe around a few hundreds, can influence how a model behaves. Research gaps indicate that there is no scalable way to thoroughly check and verify massive training datasets for hidden malicious data, and there is no reliable system that can automatically detect whether training data has been poisoned. Next is backdoors. So it is strongly active research area, and research findings indicate that hidden trigger-based behaviors can be inserted into models and work reliably in experiments, and these hidden behaviors can remain even after the model is updated or fine-tuned. Research gaps indicate that there is no reliable way to discover all hidden triggers that activate backdoor behavior. Some backdoors are intentionally designed to be so hard to notice that current detection methods cannot identify them at all. Next, adversarial inputs. It is partially mitigated. So research findings indicate that training models on difficult or tricky inputs improves their resistance. However, very long or carefully structured inputs can still confuse or break the model. So the research gap is that there is no guarantee that a model will behave correctly for every possible input, especially the complex or adversarial ones. In privacy attacks, the findings indicate that large models are less likely to reveal whether a specific piece of data was used during training. However, models that are fine-tuned on smaller or sensitive datasets can still leak private information. So research gap indicate that it is still possible in some cases to reconstruct or infer sensitive training data from model outputs. There is no strong built-in guarantee that user or training data will remain private unless special privacy preserving methods are used. Next is model extraction, that is an active threat. So findings indicate that attackers can repeatedly query a model through an API and use the responses to build a similar or clone model. So the gaps are that there is no fully reliable way to prevent attackers from approximating or copying a model's behavior through repeated access. Techniques like watermarking are still experimental and do not provide dependable protection. Then supply chain attacks, that is most under-researched area. So the problem is that training data is extremely large and often not fully visible or verifiable. So external tools, libraries, or components used in AI systems can be compromised. So research gaps, there is no global system to verify that datasets are clean, safe and free from manipulation, and there is no widely adopted standard to secure the entire AI development pipeline from data to deployment. Now let's see what researchers now realize, that is the 2025 consensus. So across multiple studies and surveys, researchers have reached some common conclusion. So the first one is that security is not just a model problem, it is a system problem. This means that even if the AI model itself behaves safely, the overall system can still fail. Security depends on full setup, including the tools, data access, APIs, and runtime environment. In simple terms, a safe AI inside an unsafe system can still cause harm. Secondly, the attacks are compositional. So one attack can turn into another. So this means attacks are not isolated. They can combine and evolve step by step. For example, prompt injection can trick the AI into misusing tools. Poison training data can make the model easier to jailbreak later. A successful jailbreak can then be used to extract sensitive data. So in simple terms, an attacker can chain small weaknesses together to create a bigger threat or attack. Next, long context is the new attack surface. So modern AI models can process very long inputs like documents, chats, etc. So attackers can hide malicious instructions deep inside large amounts of text. So the risk is that harmful instructions become harder to notice or filter, and the model may follow something hidden far earlier in the input. So in simple terms, the longer the input, the easier it is to hide dangerous instructions inside it. Finally, agentic AI increases the risk drastically. This means that AI systems are no longer just answering questions. They can now take actions like sending emails, calling APIs, or executing tasks. So the risk is that if the AI is tricked, it can perform real-world actions, not just generate text. So earlier AI could say something wrong, now it can do something wrong. Now here are some big open research gaps. So these are the major problems that researchers still have not solved. So there is no formal security theory for LLMs. This means that there is no strong mathematical framework to prove that an AI system is secure. Unlike cryptography, we cannot guarantee that the model will always behave safely. And there is no clear system to ensure that model always separates the trusted instructions from the untrusted input. So in simple terms, we cannot prove that an AI system is truly secure. We can only test and hope. There is no universal benchmark suite. This means different researchers test models in different ways. They use different prompts, different models, and different evaluation methods. So the problem is that results cannot be fairly compared. One model may look safer just because it was tested differently. In simple terms, there is no standard test to measure and compare AI security reliably. There is no reliable attack detection system. So some simple attacks can be detected, but advanced attacks are still missed. Specifically, systems struggle with multi-step attacks that unfold gradually. So indirect instructions hidden inside normal looking text. So we can catch obvious attacks, but clever and hidden ones still pass through. There is no dataset integrity system. This means we cannot fully verify that the training data is safe and clean. There is no reliable way to confirm that no malicious data was included. So the problem is that datasets are extremely large and often come from many sources. So hidden manipulation can go unnoticed. So we cannot guarantee that the data used to train AI has not been tampered with. And finally, there is no robust agent safety framework. So future AI systems will plan actions, they can use the tools and interact with the real world. Current safety methods are not designed for such complex behavior. So the problem is that existing protections work for simple responses, not for long chain of actions. We do not yet know how to fully control AI systems that act independently over the time. So if we step back, the story of LLM security is not about isolated bugs, it is about something deeper. We built systems that understand language, but we didn't build systems that understand the intent. And because of that, instructions can be faked, training can be poisoned, memory can leak, and systems can be tricked through the language itself. So LLM security is still in its early internet era, full of discoveries, patches, and unknowns. That brings us to the end of the session. Stay tuned for similar content.